Hi everyone, and welcome to EE 326, Lecture 18. Today I'm going to be discussing a technique to evaluate the frequency response of circuits when we're unsure about how the circuit's going to behave. That is, we're not sure where the dominant pole is. The technique we're going to be talking about is called the open circuit time constant technique. In your book, this is section 10.3. All right, let's get started. Okay, so here's the challenge. Up to this point, we've talked about the frequency response of amplifiers where we have a good intuitive sense of where the dominant pole is. For example, if we look at this common source amplifier shown on the bottom left, we can look at this and say, oh, okay, we have this RL here, and we have a CL at the output, and therefore we think that that's going to be the dominant pole. And in fact, we haven't even really modeled what's going on yet at the input. So in this circuit, there really is only one pole you have to worry about, and that's evident in the small signal model, where there's really only one R here, and there's this capacitance associated with it, CL, and even potentially CGD. And so the question that comes up is, what if your small signal model, what if your circuit gets more complicated, and it's not obvious that there's a dominant pole or where the dominant pole is? And if we don't have the intuition, is there another technique we can use to try to evaluate the frequency response without having to rely on computer simulations that would give us some intuition about what's happening in the circuit? And that's where this technique of open circuit time constants comes in. And so here's an example of when we might need that. So now, this is again the common source amplifier, but we've decided to include an RS here, a source resistance associated with the input. And in the small signal model, we also have this RS, right? And so now what we see is there's some RS and some sort of capacitance at the input, has CGS and CGD. And then if we look at the output node, there's also an RL prime, and there's capacitance CL. So we can see right away, intuitively, there should be two poles in this circuit. But how do we know what's dominant or what the frequency response is going to be, right? Well, one thing we could do is write out the complete transfer function of the circuit and solve for everything and look at the equations. And it actually might work for this circuit, but if the circuits get a little bit more complicated, then writing the complete transfer function gets really difficult and messy. And so we need a technique that's maybe a little bit easier than that to do hand analysis and circuit analysis. And so the technique relies on some techniques that were discovered a long time ago. And it relies sort of on this concept that we can write the transfer function of any circuit, right, in terms of a product of zeros and divided by the poles, right? So we get this transfer function h of s. And this is just an arbitrary generalization for the circuits where n is going to represent basically the number of nodes we have in our circuit. And now, if we multiply this out, right, and replace some of the variables, we can get this polynomial that represents the numerator and the denominator representing the poles and the zeros. So that's just sort of algebra at this point. But there's an interesting result here, that if a dominant pole exists, then we can approximate h of s. Just going back here for a second, if we look at h of s, right, let's look at this equation here, and we assume there's a dominant pole. And let's assume, for the sake of this discussion, that the zeros that are higher frequency, so these are the zeros that are much higher frequency, then we can approximate h of s by the following equation. What we can say is that h of s is approximately equal to 1 over 1 plus b1s. Or in other words, h of s is approximately equal to 1 over 1 plus s over omega p, where omega p is equal to 1 over b1. This is what's referred to as Elmore's approximation. This is quite old. This is actually from 1948. And again, we're assuming that the zeros are a higher frequency. And basically what we're saying is if there's a dominant pole, we're going to have, then it's really only the first term of that polynomial that matters, right? It's going to be the dominant term, and then we can approximate our transfer function by the first term of the polynomial. And now the method of open circuit time constants, what it does, it allows us to calculate what this B1 value is, or approximate, I should say, what B1 is. So if we can figure out what B1 is, then we can figure out what omega p is because of this relationship between omega p and B1, and we get an approximation for the dominant pole or the lowest frequency pole. And the way we calculate B1 is we sum up this combination, these RC products, and we sum them up over all combinations. And so the question is, well, what RC products are we summing, right? So let's just assume we're going to sum R and C, and we can refer to each RC product as tau. And so if we sum all of these time constants, or tau, and then we invert that, then we get this approximation for our low frequency pole. So the low frequency pole is essentially the inverse of the sum, 1 over the sum of these RC products. So you might be asking, well, what are these RC products and how do we calculate them? And this is where the method of open circuit time constants comes in. It tells us how to calculate those. And these are the steps we would need to take to calculate each RC product. So suppose we have a circuit and then has multiple resistors and multiple capacitors, right? And maybe some sources. The first thing we need to do is set our input signal to 0. So we set the input signal to 0, and what this means is it's a short for a voltage source, right? Or it's an open for a current source. Now we need to evaluate each capacitor one at a time. So we open circuit all the capacitors except the one of interest. And then what we do is we calculate the resistance that is, quote, seen by that capacitor, or what the RC product would be for that individual capacitor. And then we multiply this resistance by the only capacitor we're looking at, right? And that product is tau, is tau 1, for example. And then we repeat this for all the capacitors in the circuit, and then we sum all of these RC products, and we get an approximation for our lowest pole by summing 1 over these RC products. This method is remarkably accurate for most circuits. Okay, so let's move on and try to apply this to the common source example that we showed earlier. Okay, so here's our common source amplifier. Again, we've included now the source resistance RS to make it a little bit more difficult and make it more applicable to the open circuit time constant technique. So the first thing we need to do, you notice we have 3 capacitors. We have a CGD here, we have CGS, and we have CL. So the first thing we need to do is figure out what the resistance seen by each of the 3 capacitors is. In other words, determine tau for CL. And so what I'm going to do is redraw the circuit where I zero the sources and I open the capacitors, and then I can kind of get a sense of what that resistor is. Okay, so let's do that. So I'm going to redraw this, right? And we're going to short the voltage source. We get RS. We have an open for CGS and an open for CGD. Now I'm looking at this GM-VGS term, but if this is ground, then this must be ground. And that means that VGS, which would be from here to ground, right, would also be equal to 0. And so we have no voltage-controlled current source. And now we're left with just the right side of the circuit, which has RL and CL. This is RL prime and CL. And so we can kind of see by inspection now that the resistance that is seen by CL is just RL prime. So that one's pretty easy. So we can say that tau 1, well, we can say that R for CL is equal to RL prime, and that's the resistance that CL sees. So tau 1 is just equal to CL RL prime. And again, this is by inspection. Okay, so let's move on. We've got our first tau 1 for CL. Let's move on now and do the tau for CGS. Okay, so now we're looking at CGS. Again, I'm going to copy the circuit down. I'm going to zero the sources, and I'm going to open the other capacitors. And I'm going to get the following circuit. Okay, and so what do we see here? Again, this is fairly clear by inspection that the resistance that's seen by CGS is totally independent of the GM-VGS on the right and the RL prime. And so the resistance that we see is really this RS. So again, what we can say is that by inspection, that RCGS is equal to RS, and therefore tau 2 is just equal to RCGS times CGS. Okay, so now let's move on to see the last capacitor in our, this should have highlighted CGD. So we're looking at CGD, right? And the question is, what's the time constant associated with CGD? So again, let's redraw this circuit. And we're going to short our input. We're going to have RS. CGS is going to open, but we are going to have CGD. This is GM-VGS and RL prime. And VGS now is the difference in these two voltages. So now things get a little bit more difficult. It's not exactly clear what the resistor CGD sees. So we need a slightly different technique to evaluate the resistance seen by CGD. And the technique we're going to use is as follows. So we can't really see what the resistance is. So we're going to replace the capacitor with a current source and then determine the voltage across that current source to assess the resistance seen by CGD. The ratio of Vx over Ix, which is what we replaced our capacitor by, will tell us what the resistance is seen at that node. So what we need to do is solve for Vx over Ix in the circuit below. All right, so how do we do that? Okay, first thing we can notice is what this value of VGS is. We have a current Ix that's getting pulled through Rs, so we can write that VGS, well, that's equal to minus Ix times Rs, right? The next thing we can notice is we can determine what this value of VD is. How do we do that? Well, if we could determine the current flowing through RL prime, we could determine the voltage across it. So if we essentially sum these, or take the difference between these two currents, we can get the current using KCL, we can get the current flowing through RL prime. So I could write that VD is equal to IX minus the current flowing through the voltage controlled current source minus, now what is that current? Well, that's GM VGS, but we know VGS is minus IX RS, so I'm going to replace that. I'm going to say minus IX RS times GM, and now the difference of those two currents is the current flowing through RL, so the voltage is just the difference of those two multiplied by RL prime. And if I simplify this, I can write that VD is equal to IX plus IX GM RS times RL prime. And now now that I've determined VD and I know VGS, I can determine VX by just taking the difference between the two. And I can say that VX is equal to VD minus VGS, right? And therefore VX is equal to IX plus IX GM RS RL prime minus IXRS, so that would be plus IXRS. Therefore, the ratio of those two, Vx over Ix, is CDG, which would be Vx over Ix, and that's going to be equal to RL prime plus 1 plus GM RL prime times RS. If we simplify it, and tau 3 therefore is just equal to CGD times RCDG. All right, so we're getting to be close to done here. So we figured out what tau 1, tau 2, and now tau 3 are. And just as a reference, this is equation 10.66 in your book. And so now we can sum these three terms. And if we sum the three terms, I've included them all in this slide here. So we have tau 1 right here, tau 2 right here, and tau 3 right here, with each of their resistance values next to them, right? And then we can say that the omega p for this circuit is approximately 1 over the sum of the taus, which would give us this equation here, right? And now if we simplify this a little bit and rearrange terms, we get to the last equation on this slide. And so let me just be clear here. This is tau 1, this is tau 2, and this is tau 3. Now, if we look at this last equation, last equation's interesting. So we see this term on the right, which contributes to the low frequency pole, right? This term on the right. And this is a CL CGD, right? So that would be CGD and CL multiplied by RL. So this is really the contribution of the output pole, or the output node. So this is the contribution to the 3 dB frequency, or the pole frequency, from our output node. Now let's look at the other term. So what we see here is a CGD being multiplied by 1 plus GMRL, and that gets multiplied by RS. So we have RS being multiplied by this capacitor, and it's interesting that capacitor, this is actually this effect right here, is the Miller effect on CGD. So that's that large looking capacitor at the input being multiplied by the source resistance RS, and then that adds with CGS because we have the CGS there as well. So the right side, this part over here, is really from the input. So you can see we have two nodes contributing to this low frequency pole, and now either term can dominate, and it really is going to depend on which term is larger, and that's going to be largely determined by the resistance. So if we have a high output resistance like we would expect in a common source amplifier because we want high gain, then the output node is going to dominate. But if we have a very large source resistance, which may happen sometimes, even though it's not really how you'd prefer to design it, but if you had a large source resistance, then this input term could dominate, and this shows you the relative contribution to this pole frequency from both the input term and the output term in the case where we don't have a dominant pole. Okay, so that's the method of open circuit time constants. Thank you very much.